Yeah, it's going.
Okay, as a preface to this lecture, if you're here for something that's thought-provoking and well thought out, you've come to the wrong place. You've stumbled upon a realm where creativity meets chaos, insanity meets ingenuity. You've entered the Michael zone.
And the save zone.
Damn it, Zabe, you stole my line. That's me. So, we got a fun one here for you today. Multi-layer heat transfer. It's like single layer, but better. So, as you did with Sahib last video, you came to this equation, which we'll be making frequent use of, and a couple other equations. But for now, we're just going to consider a two-layer wall. So, for now, ignore this beautiful circuit I've written and just focus on this. So what I'm going to do is I'm just going to think about what's going on with the heat transferring through this wall, heat transferring through this wall, and the heat going through the whole thing. Important point to note, we are in steady state, which pretty much means that heat will not accumulate in the wall itself. So everything that comes in must go out. So the obvious conclusion you draw is that this heat is the same as this heat, which must be the same heat as this. So let's just write out what these expressions would be, and we'll go from there. So this is just K. I'm just going to just write it as K, but this is like a total overall K. The area, which isn't going to change throughout the cross section, so we'll be fine. Just writing A there. L, which is just L plus L1 plus L2. Hell with it, I'll just write that, just so that we're clear. Times the temperature difference, which is 1 minus 3. So then we're going to do the same thing for Q1, which is just K1A L1. Temperature difference is T1 and T2. Again, no one caught me, so I didn't make a mistake.
I caught you.
No, you didn't say, hey, you're looking somewhere, you're looking at your computer. Nice try. So then we can write Q2 in the same way. Now, we're just going to step back from this and go to something maybe we're a little bit more familiar with, which is Ohm's law. There's a lot of interesting connections you can make with this. Like, if you think about it, we already know the heat doesn't change throughout this. What comes here and goes through this layer also comes through this layer, and what goes through the whole two-layer wall. We can say the same thing here. Well, this current is going to be the same as the current here and the current here, regardless of the resistance it comes across. And there's also voltage drops, or if you think about it, temperature drops. So keep that in mind. We'll be coming back to this analogy just a little later. So we want to find what this is equal to, what Q is equal to. Now, we can't just use this equation I've written because we kind of don't know what that K is, because it's not this material property and it's not this material's property, it's somewhere in between. So what we're going to do is we're just going to try to find something that gives us this temperature drop, and we'll just call it a day. So what we're going to do is we're just going to solve for these temperature differences and then add the two of them together. So what we will get is Q1 L1 over K1A is equal to T1 minus T2 Q2 L2 K2A is equal to T2 minus T3. Add these together, I'll pull out the Q so I don't forget to do that. And then, so basically what we have is K1A plus L2 K2A equals T1 minus T3. And so, Q is simply equal to the temperature drop divided by K1A plus L. Oh, screw it. Oh, I'll stop talking while I'm writing. L1 over K1 plus L1 over K1A plus L2 over K2A. Which, if we take a step back to this, I'm going to refer to this a lot actually. It's quite useful. If you think about it, it's like saying, okay, I is equal to V1 minus V3 divided by R1 plus R2, right? A current, which is just something that's flowing through the material, is equal to a voltage drop, in this case it's a temperature drop, divided by the resistances. These are electrical resistances, these are thermal resistances. And so if you've also noticed, these are in series. Well, guess what? So are these. This is the thermal resistance, this whole term. This is the thermal resistance of the first wall. This is the thermal resistance of the second wall. And basically what that means is that this is how hard it's trying not to conduct heat. So that's about all for this example. I'm going to move on to bigger and better things. Well, maybe not better, but definitely more complicated ones. So I'm going to leave this example up here just so we can compare to it later. I will draw something here, I think, that will do fine. And so now we're going to show what happens if they're parallel heat resistances. So in this case, the appropriate schematic, if we're going to the electrical analogy, is something like this. And you know what? I don't care. I know my resistors are awful, but I'm the one with the marker. I'm going to draw them the way I can, which is terrible. So let's just leave it at that for now. So we got parallel resistors, which pretty much means that if we have a current here, we're going to have two different currents here. Okay, and they'll both add up to this current, which coincidentally, let me finish my drawing here first. Coincidentally, that's exactly what happens, because if you think about it for just 1 second, we have this top block and this bottom block have different K values. So the heat flowing to this one has the same temperature. That's one for the blooper reel. Okay, so if we think about it, we look at this equation we have, they have the same temperature drop, the same area, and the same length. The only thing they don't have is the same thermal conductivity, meaning that these two cannot be the same value. So what we're going to do to find our overall Q is just add them together. I know it's simple, isn't it? Or it's just looks simple. So pretty much we're just going to expand this out to what it says up on the good old board up there. I'm just going to actually just factor out the temperature difference, like so. And then that's it. There's no fancy tricks on this one, although it's normally nicer to write it as this. Let me try to do it over here. Q is equal to T1 minus T2 over, see if I remember this, I think I do. I know, this is going to look really, really strange. But let's just see what happens. So let me think, did I do this right? Flip these up, put that up there. Yes, that's right. Okay. So what I did was basically just rewrite this term. Now, Michael, why would you do such a stupid thing like that? Well, it's not at all as stupid as some of you probably think. So if we go back to our lovely physics analogy, you will recall that REQ, 1 over REQ is equal to 1 over R1 plus 1 over R2 for a parallel set of resistors. So we can kind of see where the method of my madness was here. So the 1 over the -1 thing, which I'm just going to redraw this so you actually know what I'm talking about, looks like this. So this whole thing is to the -1. And that's basically saying that the equivalent thermal resistance is just flipped upside down. The 1 over the actual, R1 and R2 are these terms here. And again, no one caught me, so those should be 2's. But the basic idea is just we are having analogies with the electrical system, even though the mechanism is completely different. Okay, phew. Now I can finally breathe. So, now that that's over with, let's move on to the final step, which is, I think, a little bit more straightforward than what we just did. So, pretty much what I'm going to do is just kind of go back to this picture, but instead, I'm just going to redraw it because I don't want to erase what I already have. So the only thing that we're going to do differently here is that we're going to have T1, we're going to have a T2, we're going to have a T3, but if you think about it, we can't just stick a thermometer right here and measure this temperature because, well, for one thing, you're going to affect the heat flow throughout the whole sample because you're giving it another path to go through. It's going to have to decide almost, do I want to go through this wall or do I want to go through the thermometer? And so normally what we just do is we kind of just take an air measurement. And so we've already talked about heat transfer through the air. It's called whatever, time's up. It's called convection. So, well, all we're going to just do is, oh dear, I didn't write that down, but basically what we just found out was that the general case is that the heat flow is equal to the temperature difference divided by the sum of the resistances. If you think back to what we did with this problem, you'll see that we had R1 plus R2 in the denominator, and we had a temperature difference on top, and it also drew very nicely to Ohm's law, which I had up earlier. So, pretty much what I'm just going to do is write down my resistances, and that's it. So the first resistance is the thermal resistance due to conduction, and that's just 1 over H1A. The reason I know that is because convection flows like this, very similarly to conduction. So you know that if this is I, this is our V term, then this has to be 1 over our resistance for this to be accurate. If you just try to rearrange it, like just divide by HA, you'll see it makes sense. So then R2 is of course LA over K1. That's basically what we've gone through already. R3 is L2 over A, K1, K1, K2. And then R4 is just 1 over H2A. Now the reason why I put H1 and H2, well, that implies that they're different, and they could be. Like if this is our interior wall, and we have a ceiling fan going on, then you could have forced convection here, which would change the resistance of of heat travels, heat transfers. And if we have just a breeze out here, the different wind speeds might change how the heat is transferred from T0 to T1 and from T3 to T4. So pretty much all that would be left to do is just put all of these terms, sum them up here. You have your temperature differences, so you can find the heat flow or anything else that you would need to find. And I believe that's a wrap. Yep. Oh. That was a tough one.